Hello, my name is Angelina Dominguez, and I teach AP Computer Science Principles at Veterans Tribute Career and Technical Academy in Las Vegas, Nevada. I'm excited to be talking to you today about binary numbers again. So let's look at what we're going to learn today. Our main objective today is to talk about the consequences of using bits to represent data. Specifically, things such as overflow and round-off errors. So let's get started. So imagine working with a math problem by hand, but you could only use numbers 1 to 10. Anything higher than 10, and you had to round down, or you simply couldn't calculate it. How would you then report the answer to 5 plus 6? 11 is out of bounds of your range, so you would have to round the answer down to 10. Well, what about 8 times 9? 72 is way too large to round down to 10 because those results aren't even close. So you just wouldn't be able to report the answer. How would this affect your ability to calculate important things like paychecks or measurements or times? Well, luckily for us, the above scenario isn't something you would normally encounter in your everyday life. However, computers have to deal with these types of constraints all the time. You might recall that binary is data that's represented by ones and zeros, arranged in groups called bytes. This includes numbers too, like integers, whole numbers, even odd and even numbers, including zero. In programming languages that are interpreted by computers, integers are represented by a fixed number of bits, which end up limiting the range of values that a computer can read and work with. The commonly used bit length for integers are things like 8-bit, 16-bit, 32-bit, or even 64-bit. Depending on how many bits your computer or your program is using, will determine how many different values of integers your computer can store in its memory. And if you end up needing to store more values than you have room for, well, you start getting some errors. For example, some programming languages store values in up to 32 bits, or 32 ones and zeros, which in simple terms is just 4 bytes. Now, 4 bytes ends up allowing us to represent a little over 4 billion different values total. This means that once a computer has more than 4 bytes worth of data, well, again, there's going to end up being some problems. Now, I know a little over 4 billion may seem like a lot, but think about this. Are there more than 4 billion numbers in the universe? Obviously, yes. But a 32-bit computer can only count as high as 4 billion. You could count to infinity if you had the motivation and the time, but a computer would have to stop at a certain point because it is limited and it doesn't have a way to represent those numbers past its fixed number of bits. So a limitation on the amount of values available will limit the kind of calculations our programs can do. If the program encounters a calculation that requires a larger number than what is in its memory, or than what its memory will allow it to store, this can result in something called overflow. An example of overflow in real life would be, think of an old school car odometer when it reaches its maximum value of 999,999 miles. But the car continues to be driven. Once the car has gone 1 mile more, the odometer will essentially reset because it cannot represent numbers higher than 999,999 miles. And then the odometer would read 1, yet we know it's been driven more than 1 mile. Programming languages also have problems with some real numbers. Take pi, for example, that continue on towards infinity. Since a fixed amount of bits is used to represent these numbers, the full infinite value cannot be represented and thus cannot be used to calculate. Instead, these numbers are rounded to the nearest number that can be represented with the fixed range, or within the fixed range, actually. This can result in rounding errors or even errors in compiling. Take this example. Say we have one computer made by manufacturer A, and they have this computer computes pi with just the first two decimal points of pi. So they use 3.14 when doing calculations. While manufacturer B may have their computer calculate pi with a couple more place values, 3.1415. When doing math with these two different computers, these will result in two different outputs for the same problem, which is not good because we rely on 2 plus 2 being 4 every time we do that calculation, regardless of what computer program we're using. Here's another way to look at it, a visual. Let's say you have a limit of 4 bits represented here with this pie chart, but you end up needing to represent the value at the red line. What do? What will your computer do? It can only hold 4 values, not something in between. So a computer might round, but how? Will it round up? Will it round down? Either way, the rounded value isn't very close to the original that we needed, and we end up with a round off error. If we had more bits, like this, maybe say like 8, the computer would still have to round, but you can see that the value it will round to is much closer to the original red line that we wanted originally. So the more bits we have, the more integers we can represent. In an ideal situation, the range of numbers a computer can work with would only be limited by the computer's available memory. When writing pseudocode, the assumption is that all mathematical operations are not only possible, but will also yield highly accurate results because no numbers will have to be rounded and no calculations will result in an overflow memory. In the real world, though, this is not always possible. If a number stretches on towards infinity, then theoretically, it would require an infinite amount of computer memory in order to store and calculate with. This is just not possible. Let's see an example. Computers represent all data with bits. So we know that ultimately, each of these numbers is a sequence of zeros and ones. So to start simple, let's imagine a computer that only uses 4 bits to represent integers. It can use the first bit in this first column to the left to represent the integer or to represent the sign of the integer so that we know it's either a positive or a negative number, and the other 3 bits for the absolute value. In that number system, the number 1 would be represented like this, like you see on your screens, 0001. Again, that first column represents the sign, in this case a positive number, and the 1 in the rightmost column would represent the 1's place value. So what's the largest number this system could represent? Well, let's fill in all of the 1's and see. So this is going to give us positive number 7, since 2 squared plus 2 to the first plus 2 to the 0 gives us 4 plus 2 plus 1, which equals 7. So our very simple computer can only count to 7. So what would happen then if we ran a program like this on this simple 4-bit computer where the largest positive integer is 7? The computer can store the variable x just fine. X is getting the value of 7. But y is 1 greater than the largest integer that this simple computer can count to with our fixed number of bits. In a case like this, the computer might report an overflow error or display a message like number is too large. It might also truncate the number, capping all results to 7, or maybe even wrap the number around like that odometer example so that 8 ends up becoming 1. Fortunately, most modern computers use 64-bit architecture, which can store incredibly large numbers in order to represent data. But at some point, the computer still has a fixed number of bits to work with. We've reached the end already. That was so quick. So what should we take away today? So we talked about the consequences of using bits to represent data. And again, specifically, we looked at overflow errors and rounding errors. And that's it for today. Hope to see you again. Bye-bye.